Hello, everybody. For this week, we'll be talking about complexity. This is the topic that naturally follows the topic of counting, in which we try to use different principles to count the numbers of operation or computational effort. But complexity allows us to compare different algorithms more objectively. And we can actually put different algorithms according to the complexity classes, which we're going to define later in this class. In terms of references, we have a course reserve textbook, just in case that you would like to read further into this particular topic, which is up here. And we also offer 4 different links to one of the most important concepts that we're going to introduce today, which is the big O notation. Just in case that you feel that the slides explanation is not clear enough for you, you can click into those links to get more reading. Finally, we also will introduce one programming tools that I feel will be very helpful, particularly if you're learning about how the Python program works. This particular website is called the Python Tutor. We will go over that when we have our in-class session. The whole complexity lesson for today will be divided into 3 parts. We will start by revisiting the design principle of algorithm, and then we talk about how we can measure the efficiency of different kind of algorithm. Then we will move on to the definition of the big O notation. How do we use the big O notation in particular to implement this previous idea where we have the measurement of efficiency. Finally, by using the big O notation, we'll introduce different type of algorithm class, just to tell you what are the most common type of complexity that we will be able to see, not just in this class, but beyond this particular class. You look into the real world problem, you look at real world algorithm design. What are the complexities that are out there? So as a start, let's look at something that potentially will be difficult to solve. This is taken from the 2018 Winter Olympic. Just like all the Olympics in the past, before the Olympic happened, there's a torch relay. In this particular year, this is a very complicated operation. In total, there are 80 cities that need to be included in the South Korea. So in total, you have a lot of runners, as you can see from here, more than 7,000, close to 7,500 runners. Very long distance that you need to travel. So one of the questions that you need to come up with is that you have all these 80 different locations. How should you decide the order in which you should visit those locations? Of course, I mean, you can come up with all the different kind of ways where you aim to achieve. For example, your objective may be to minimize the distance, which is a very common objective among this type of operation. So let's say this is your goal. In the case where you do not have very clear idea how the problem can be solved, as we have illustrated in the previous weeks, it's always a good idea to begin by doing the pure enumeration. Right, so if you have seen like all the possibilities out there, and for each and every possibility, you actually try to calculate their distance, then guaranteed you should be able to find the so-called optimal route. But the problem here, of course, is that there's a huge amount of combination. Just to give you a rough idea how large it can be, we start with the first choice of the city. You have in total 80 possibility, so you will have 80 as the first choice. Now you have picked the first one. If you look at it, the next city that you can choose from is reduced by 1, so you have 79. And you keep multiplying these numbers of choices until you reach the final destination. Right, so in total, you have 80 times 79 times 78 all the way until 1. That is 80 factorial. And we know that factorial grow very, very fast. So for 80 factorial, this is 10 to a power of over 100. So even you have the quickest computer in the world, you are not going to solve this particular problem. This is what we mean by a problem being very complicated. Really, even in the case where you have supercomputer in the world, you cannot solve this kind of problem. So before we go into the definition of the complexity of the algorithm, let's do a little bit of recap what we mean by algorithm. Algorithm basically means that you have a very detailed description about how to go from input to the output. And you need to be very specific. You cannot, again, leave any vagueness because in the definition, because eventually we know that the algorithm design need to be implemented. And without a blueprint, very exact blueprint, you cannot do the implementation. So visually speaking, it's as if on the left-hand side, you have a whole bunch of input. On the right-hand side, you tell the user of the algorithm what can be expected. And then the algorithm will fill in the blank that's connecting the inputs to the output. That is what the algorithms are being designed for. That's essentially a sequence of steps and operations that we aim to achieve our goal, reaching the final output. Our goal over here is that we want to make sure that our algorithm is simple yet precise. So again, over here, as we have illustrated in the past, algorithm doesn't need to be a computer program. Starting from very ancient times, thousands of years ago, people are already designing algorithms. It's just that at that time, everything is manual. You don't have computers, right? But you have all the necessary properties that we are talking about over here. Right? Of course, now we have much more powerful computational tools. So our algorithm, when we define that, usually we have in mind that eventually it will be implemented on a personal computer. Okay, so what exactly do we mean by having a sequence of simple and precise steps? That actually refer to like a couple of important property we want to see in our algorithm that we have highlighted in the earlier weeks. Being precise basically means that you should write the instruction in the way that everybody, particularly the user, will be able to understand. Being effective basically means that if possible, if you have multiple alternatives, you want to reach the final destination, you want to reach the final output as fast as you can. Finally, I think very important thing is that you want to make sure that your algorithm design is practical. One, I think, perfect example just to show how you can design hypothetically perfect algorithm but completely useless algorithm is to say that, for example, when you design a chess playing robot, you can ask this particular program to simply just choose the best step. But without going into detail, what do you mean by the best steps and how do you derive that? Right? So, I mean, if your algorithm have all this property, we say that this is a very well defined. And this is the kind of, I think, mental diagram we always try to propose. On the left-hand side, you have input. On the right-hand side, you have output. And then algorithm sit in the middle. That is a black box. You try to fill in the detail such that you can very effectively and efficiently go from the left-hand side to the right-hand side. Now, the reason why we would like to conduct a complexity analysis is that usually there are definitely more than one way to achieve this objective. So how do you pick the right one? How do you pick the good one? That is what the complexity analysis is meant to achieve. Next, we have a very concrete example, which is the finding of the greatest common divisor. So just like what have been proposed last week when we introduced the fundamentals of algorithm design. We have went through this process where we can use this sieve algorithm to generate a list of prime numbers. So the determination of the greatest common divisor is actually related to this kind of a pursuit of the prime number. So also quite ancient, right? You can see that this is also from the Greek times. So we want to find the greatest common divisor of two numbers, and the definition is actually over here. right? So if you look at the definition, two numbers are not prime to one another. When we want to find the greatest common measure or greatest common divisor, that essentially means that that will be the largest number that can be used to divide both number perfectly. So some simple example, for example, if you like to find the GCD of 4 and 8, that will be 4, right? So I mean, just very simple math. Right? Most, I think in your prior years of schooling, you should be able to solve this already. So we can make it slightly more challenging. For example, the GCD of 81 and 36. Again, you can do a little bit of calculation and you'll find out that the GCD of these two numbers will be 9. But how about these big numbers? 1989, 867. It's not so easy anymore, right? So this is where algorithm will come in. We want a systematical way to solve the cases even when the cases are really very large and it's beyond mental calculation. How do we do it? So to pose this particular problem formally as an algorithm design problem, we have to identify what are the input. In this case, very well defined. We want A and B both should be non-negative integer. So you can see that we are very specific over here. And then the output will be the greatest common divisor of this particular two number, following our previous definition. Algorithm right now is still a big question mark because again, anything as long as it works, it can go into it. We will analyze a couple of alternatives later. So the first algorithm, again, just like before, whenever we do not know how to solve a particular problem, we start with the brute-force algorithm, which basically means that we like to try out all the possible solutions. So a very simple way to achieve that is just like what's being stated over here. If you have two numbers, A and B, the greatest common divisors should be between 1 and the minimum of A and B, right? If you try out all the possibility, eventually you should be able to find the GCD of A and B, right? Very simple approach. And we will see how do we put it down exactly following our previous specification of being as precise as we can. So we use the same format, input, output. These two parts doesn't really change, but the algorithm part, now we fill in the detail. We start with the step 1. We set T to be the minimum of A and B because any number that's greater than either A or B cannot be the GCD, right? And after we have determined which number of A and B is smaller and we set it to be T, we'll repeat the following two steps. Step number 1, we will check whether or not A and B are both divisible by T. If that is the case, it basically satisfies the requirement of the GCD. We'll return that as an answer. Otherwise, we will subtract 1 from T. We basically make T to be T minus 1, a slightly smaller number. And then we continue to check. Eventually, I mean, even in the case where A and B, they are prime to each other, we should still be able to terminate the algorithm because the smallest possible GCD in that case will be 1 if both numbers are prime, right? So with this very simple, I think, check, you will note that this is very precise algorithm. You can implement that, and you know that given enough amount of time, eventually this algorithm will come to a stop, and you guarantee will have the correct answer, which is the greatest common divisor. As an example, you can look at 81 and 36. The smaller number is 36, so that will be your T. You start from 36. You try to see whether or not 36 can be used to divide 81. It turns out to be no, right? So following the process, you'll reduce the value by 1. So now the value becomes 35. So you continue the process until eventually you reach number 9, which is the final solution. So it takes you 28 steps, right? So that to us is one way to measure how efficient this particular algorithm is. If this is the only way that we can solve the problem, then there's no comparison. We have to take it, whether or not we like it. But luckily, we have another alternative. This is called Dijkstra's algorithm. It's proposed by Dijkstra, a famous mathematician, make a lot of contribution in the algorithm design. So he actually made this very fundamental observation to say that GCD of two numbers will not be changed if the smaller number is subtracted from the larger number. So as an example, if you have A and B, let's say A is greater than B, then the greatest common divisor of A and B will be the same as the case where you subtract B away from A and then the B itself. If you put it in the numerical terms, right? So again, we repeat the case of 81 and 36. You see that 81 and 36, GCD of these two numbers will be the same as 81 minus 36 and 36, right? So you get 45. And you will just keep repeating this process, right? 45 minus 36, you got 9. And these two numbers not the same, so you continue, right? 36 minus 9, minus 9, minus 9, until two numbers are the same. Then you will return that number. That number will be your greatest common divisor. So as you can see from over here, the steps are now much, much shorter. Okay, so let's see if we try to express this modified and more efficient version of the algorithm, how do we represent that? So we have A and B. So we repeat this following two steps until A equals B. If A is larger than B, then we subtract B from A. Otherwise, we subtract A from B, right? So very simple process. And we will just keep doing this until A equals B, at which point we'll return A as an output. So using exactly the same example, 81 and 36, we can count the numbers of steps it takes you to eventually reach the final step. And as it turns out, you only need 5 times, 5 steps, much more efficient, right? So this is probably a very simple exercise. Now we have two algorithms and we have a definition on the effectiveness of the algorithm, how efficient the algorithm is. We can actually try out different examples. 8136, this is the example we have already tried out. We know that is 28 versus 5. Now what we are really curious about is if we just keep increasing A's value, B's value, what will be the numbers of repetition? So if we actually implement this two version of the algorithm, which by the way, you're going to do it in the next lab 1. So we will see that the numbers of repetition stay quite big for the brute force method. And actually, as the numbers of A and B increases, the amount of effort for the brute force also increases. But on the other hand, if you look at the Dijkstra's method, it actually scales very well. Even in face of very large A and B value, is still quite efficient, right? You only need a small numbers of steps and you can reach the final answer. So how do we, with this particular example, right, what kind of insight can we get out of it? How do we use this insight to define a good algorithm? Right, so we have two different aspects. I think number one is actually the most important aspect. We want to make sure that the algorithm is correct, right? After all, what's the point of having an incorrect algorithm that can generate solution very, very fast? It's very efficient. It generates solution very, very fast, but the solution cannot be used, right? So the number one priority is always the correctness. But after we can always guarantee ourselves that we get the correct answer, we can actually go for efficiency. There are two different types of efficiency. Both will be touched upon within this course, but for today's lesson, we will focus on the speed, which is the efficiency in time. But in the later weeks, when we reach the data structure session, you will note that actually we also care about the way we store information. In other words, how do we make sure that when we design the approach, we don't use so much storage space? Okay, so here are some of the examples about like how not to measure the efficiency. So when we say the efficiency of an algorithm, is actually not about the programming language. It's not about the language that we actually use, not about like C++, if you have heard of that. It's not about Java, not about Python, right? So the measurement of the algorithm should really be independent of the implementation, the language that's being used. It should also be independent of the hardware. For example, PC versus Mac, or what kind of CPU that's being used is Intel i5, i7, or Mac M1, M2, so on and so forth. It's not even about like who implemented this algorithm, right? So maybe Andy implemented one version, Barbara implemented another version. So we are not comparing the efficiency of their implementation or the amount of data we actually use. The efficiency, in other words, should be purely based on the algorithm itself. And then in terms of complexity analysis, we are particularly interested in the response of your execution time to the input size, right? In other words, we want to find out that what will happen when the input size begin to scale up. You have n equals to 100, 1,000, a million, a billion, so on and so forth, right? We want to see that under these kind of circumstances, how will our algorithm perform, right? So this is one example. So about like the ways that we can begin to quantify the complexity or the effort of a particular algorithm. This algorithm is actually very simple. We want to find the maximum element within a particular list A. We have just covered lists last week, right? So we know that list is a collection of a sequential collection of a lot of elements. In this case, the elements are all like numbers, right? So we have in total n numbers. So inside this particular program, you can see that this is the way that we can find the max sequentially. We like the max, which is the temporary storage of the number, to be the first element. And then we iterate through the second element until the end of the list. Whenever the max is actually smaller than the current element, we'll replace the max. So you can see that we actually color the key operators in different color. The green over here, this is what we call the comparison operator. It compares two numbers. This is one type of operation. So we can count the total numbers of operations that will be engaged. So we start from 2 all the way until n-1. So you have n numbers. In other words, when we make the comparisons, we should have exactly n-1 comparisons, because 2 is compared against max. The second element is compared against max. The third element is also compared against max. You do this all the way until the nth element. You start from 2, you end at n, so you have n-1. And the numbers of assignment, this one, if you look at over here, is actually variable. Right? So sometimes it can be large, sometimes it can be small. If the true maximum occur at the first location, then you only have one assignment. But if let's say the number is actually in increasing order, then the assignment over here will be executed in after each and every comparison. So this is the reason why we write it this way. We say that we don't exactly know, we cannot be certain how much it will be, but it will be at most n. Okay, so in other words, we try to look for the worst case scenario. In the worst case, you will have n. Right, so let's look at some examples. So in these two class exercises, we will provide you with the exact code. You will follow the code and you will try to follow very similar steps to come up with your estimation of the operation. For the very first one, you are given a list A of n numbers. The value of n is greater than 10. and you want to find out which of the first 10 number is the largest. This is the code that will help you achieve that. And your task over here is to identify what is the numbers of comparison, the green operation, and numbers of assignment, which is the blue operation. This is the first one. The second question is given an array again of A, you contain n numbers. You want to find the smallest difference between any two numbers in the list. So again, the code over here is provided to you. You have a slightly more operation now. We have three colors. We have comparison, you have assignment, and you have subtraction. Again, use n as a unit, and you try to quantify the numbers of these three different operations. Give yourself some time, work on that. We will come back with a solution in a separate video.